Deep in the constellation Leo, 120 light-years from Earth, a telescope has captured something that will change everything we thought we knew about life in the universe. The James Webb Space Telescope has detected a world where the temperature holds steady at exactly 49 degrees Celsius, 120 degrees Fahrenheit, wrapped in an atmosphere that pulses with the chemical signature of living creatures. Scientists are 99.7% certain they've found it, a planet teeming with life more habitable than Earth itself. If you're interested, subscribe and be part of the search as we uncover the world's signals and stories written across the stars. The numbers arrived on a Tuesday morning in December, hidden within streams of light captured by the James Webb Telescope. At Cambridge University, astrophysicist Niku Madhusan stared at his screen, watching the faint dips and rises of light that had travelled more than a century across interstellar space. Each curve was a clue, a hidden story written in photons. Then came the anomaly, a single molecule that shouldn't have been there, dimethyl sulfide. On Earth, it's produced only by life, by plankton in the oceans, bacteria in the soil, and the metabolism of countless unseen organisms. It doesn't form from volcanoes or lightning or mineral reactions. Only biology makes it. The signal wasn't faint. The probability of error was less than 3 in 1,000. Madhusan's hands trembled in excitement. Somewhere, 120 light-years away, something alive was showing itself in void of the cosmos, the world named K218b, that produced the signal orbits around a small red dwarf in the constellation Leo. It's about 8 times the mass of Earth, large enough to hold a deep atmosphere but small enough to avoid becoming a gas giant. For years, astronomers assumed such worlds were too hostile for life. Their thick hydrogen blankets, their crushing gravity, it all seemed unwelcoming. Webb's data told a different story. Beneath that dense atmosphere, the temperature holds at around 49 degrees Celsius, 120 degrees Fahrenheit, warm but gentle enough for liquid water. The hydrogen acted as a perfect insulator, trapping heat and redistributing it evenly across the globe. Madhusan's team had been studying the planet for months, capturing the faint starlight that passed through its atmosphere each time it crossed in front of its star. Each transit revealed more. First water vapour, then methane, then carbon dioxide. A cocktail of gases that together painted a picture of balance and stabilisation. And finally came dimethyl sulfide, the unmistakable scent of life. In astronomy, certainty is rare. Most discoveries are whispers of possibility, easily overturned by later data. But this one carried 99.7% confidence, a level of statistical strength usually reserved for the discovery of subatomic particles or gravitational waves. For the first time, humanity wasn't just guessing. We were almost sure. The planet's thick atmosphere acts like a planetary greenhouse, but not a hostile one. Instead of trapping destructive heat, it creates thermal equilibrium. Water neither freezes nor boils, it simply exists, vast, deep, and stable. Such a world would be paradise for chemistry. Life would not need to fight against droughts or winters. Evolution could unfold continuously, like a melody that never stops. Its parent star burns faintly compared to our Sun, small, steady, and nearly immortal. Red dwarfs live for trillions of years. Their flames are soft but eternal. Around such stars, time itself becomes generous. Any spark of biology that begins there might have ages beyond imagination to grow, adapt, and transform. When the first results were announced, the scientific world paused. For decades, we'd searched for Earth's twin, a rocky planet orbiting a yellow star. Yet here was something entirely different, and somehow even better suited to life. It wasn't something very similar to Earth. It was a new category of habitable world, vast oceans beneath alien skies, life sustained not by resemblance to us, but by the universe's own creativity. To see such a world, Webb had to perform miracles. Suspended 1 million miles from home at a gravitational point called L2, the telescope lives in permanent darkness. Its 5-layer sunshield, the size of a tennis court, keeps it colder than the surface of Pluto. 18 golden mirrors, each a hexagon of perfect geometry, collect light invisible to our eyes. Together they create a mirror so precise it can detect the warmth of a bumblebee on the moon. When that distant planet drifts in front of its star, a fraction of light filters through its atmosphere. Molecules in that air absorb specific wavelengths, leaving faint imprints, a spectral fingerprint. By decoding those patterns, Webb reveals the planet's chemistry. It's like identifying a voice by its breath. But detecting that whisper is unimaginably difficult. The host star shines billions of times brighter than its planet. To overcome that, Webb uses its coronagraph, a mask that blocks the star's glare, like holding your thumb over the sun to see a firefly nearby. The remaining starlight is filtered, analysed, and stripped of noise by algorithms so precise they can separate a handful of meaningful photons from millions of empty ones. Those photons carry stories older than memory. Each one left its homeworld 120 years ago, around the time humans first learned to send radio waves into the sky. Now, a century later, it tells us that life was already thriving elsewhere. It's humbling to realise we're not discovering life as it begins, but as it was. A century-old echo of a living planet that has likely continued ever since. The atmosphere revealed even more than chemistry. It revealed behaviour. Methane, carbon dioxide and water vapour formed a delicate balance, a kind of planetary metabolism. On a lifeless world, such gases would quickly react and stabilise into chemical equilibrium. But equilibrium wasn't what Webb saw. Instead, the ratios fluctuated, a chemical disequilibrium, the same signature that defines Earth's living air. Life doesn't allow balance. It constantly reshapes its environment, breathing, consuming, exhaling. Even the planet's missing gases told a story. If it were lifeless, its skies would be filled with ammonia. But ammonia was almost entirely absent, as though something were using it, converting it, cleaning the air. On Earth, microbes do exactly that. The deeper the analysis went, the clearer the picture became. Not a sterile world, but a thriving one. Not a fluke of chemistry, but an ecosystem on a planetary scale. Statistically, the confidence was overwhelming. A 3 sigma detection, 99.7% certainty, meaning the chance of error was roughly 1 in 1,000. In any other field, that's beyond question. And yet, no number could capture the enormity of what it implied. For centuries we'd asked whether life existed elsewhere. Now, for the first time, the answer was not speculation. It was measurement. To reach that conclusion, Webb had to detect molecular patterns only a few parts per billion in strength, the spectral equivalent of hearing a heartbeat through a hurricane. Light was measured to 1 part in 10 million, each wavelength recorded and compared, every alternative explanation systematically ruled out. Contamination from Earth? Impossible. Random noise? Statistically negligible. The simplest explanation, the only explanation, was biology. That's why the moment the data was confirmed, every scientist who saw it felt the same quiet weight. This wasn't just an exoplanet. It was the end of cosmic solitude. The planet's vast oceans, hundreds of miles deep, blur the line between sea and sky. The water mixes with hydrogen, creating a liquid that stays stable over a staggering range of temperatures. Such chemistry could nurture life forms beyond imagination. creatures that breathe hydrogen instead of oxygen, feeding on methane instead of sunlight. Under its perpetual clouds, pressure builds into conditions we can barely simulate. Diamonds may form and rain through the atmosphere, glittering down into the oceans like frozen stars. Somewhere below that luminous haze in the warm twilight waters, life is almost certainly stirring. Not fragile, not temporary, but ancient and abundant. This realization changes everything. If biology can thrive in hydrogen seas around a red dwarf star, then life isn't rare. It's inevitable. 3/4 of the stars in our galaxy are red dwarfs, quiet, enduring suns with planets just like this one. If even a fraction host biospheres, then our Milky Way is overflowing with living worlds. The discovery redefines what habitable means. It tells us that life doesn't need an Earth clone. It only needs balance, the right chemistry, the right temperature, the right patience. Webb's golden mirrors did more than observe. They connected us to another chapter of creation. Each photon it caught carried a whisper across space and time, the breath of an unseen ocean, the sigh of life beyond our reach. In that faint light, humanity found proof that existence is shared, that we are not the first, not the only, and certainly not the last. The universe, it seems, has been alive for more time than we can logically imagine. The red dwarf at the heart of this system is small enough to fit inside Jupiter, yet dense enough to hold a planet like K218b in its gravity for eternity. Its light is dim, a deep ember red rather than the fierce white of our sun. To human eyes it would not blaze, it would glow, soft, constant, patient. This is not a star that lives fast and dies young. It burns slowly, almost tenderly, stretching its lifetime not into billions but trillions of years. In the scale of the cosmos, it is nearly immortal. That longevity changes everything. Around our sun, light shifts, climates wobble, and extinction follows extinction. But here, the light remains steady. The same warmth, century after century, millennium after millennium. No wild flares to strip the air, no chaos to undo the work of chemistry. For a world like K218b, that constancy means something extraordinary. Oceans that never freeze, clouds that never vanish, and time, endless time for life to rise, adapt, and endure. For decades, scientists dismissed red dwarfs as unfit for life. They are small, cool, and their habitable zones lie so close that any planet must orbit almost hugging the star. But what once looked dangerous turns out to be ideal. K218b completes a year in just 33 Earth days, close enough to feel the warmth of its dim sun, yet far enough to remain calm. One side always faces daylight, the other sleeps in darkness. From space, it would look like a glowing marble, half bathed in crimson light, half wrapped in shadow. Yet even that night side is not cold. The planet's thick hydrogen atmosphere acts as a vast conveyor of heat, moving energy across its skies. That stability is rare in the universe. It gives water permanence, allows weather to flow without violence, and provides chemistry with peace. If life exists there, it evolves beneath a sun that never rises, never sets. A world caught between dawn and dusk, where the line dividing day from night is not a frontier but a habitat. Under that eternal twilight, the colour of the sky would never be blue. It would burn in layers of crimson, violet and copper, dim but endless. The star would hang motionless above the horizon, fixed in the same spot forever. The oceans below would reflect that red light, glowing faintly as waves move under a horizon blurred by haze. On the night side, darkness would not be absolute. The dense air would scatter the star's glow, painting the blackness in faint metallic hues. Even there, light would linger. The glow of auroras, the the shimmer of lightning inside distant clouds. This is not a planet of contrast, but of gradients, one where everything shifts smoothly, never abruptly. If evolution began here, it did so with patience. On Earth, life was shaped by disaster, impacts, ice ages, and sudden burst of fire. But around this quiet sun, there are no mass extinctions, no sudden ends. The rhythm of time is slower, the canvas broader. Life here could grow old without interruption, carried forward on the calm breath of a red dwarf dawn. Webb's instruments were born to see in this kind of light. Infrared, the very wavelength red dwarfs emit most strongly. That is what made K218b signature so clear. The telescope wasn't straining to see something faint. It was tuned to the exact language of the star itself. Every beam of infrared carried within it the code of the planet's atmosphere. The heat of clouds, the scent of oceans, the breath of unseen organisms. Each time the planet crossed the face of its star, a tiny fraction of starlight slipped through its air. Molecules absorbed that light at precise wavelengths, leaving faint notches, spectral fingerprints. Webb read them like a diary written in light. The pages spoke of water, methane, carbon dioxide, and finally, dimethyl sulfide, the mark of life. To human eyes, the red dwarf would appear unremarkable, barely visible in the night sky. Yet that very dimness makes discovery possible. The smaller the star, the easier it is to see its planets. The glare is reduced, the signals are cleaner. What seems weak is, in truth, perfect. Red dwarfs are not obstacles. They are cosmic magnifying glasses, revealing the faint whispers of their worlds. If we could stand on one of K2-18b's high plateaus and look up, the view would be surreal. The horizon would curve beneath a bronze sky. The air would shimmer with heat. The sunlight would feel soft, more like warmth than brightness. Shadows would be long and lazy, stretching forever. The concept of day and night would fade, replaced by slow shifts in tone, in temperature, in the heartbeat of the planet itself. Life, if it exists there, would move differently. Plants might be dark, black, indigo, or deep violet, absorbing every stray photon of red light. Photosynthesis would be slow but steady. The creatures that graze on them might sense the world through vibration or pressure rather than sight. Nothing would hurry. Energy is scarce, but time is infinite. Evolution would reward patience over speed, endurance over aggression. The red dwarf's greatest gift is moderation. It burns with discipline, never wasting, never surging. While our sun will expand and die within 5 billion years, K218's parent star will still be glowing softly when the Milky Way has changed beyond recognition. For the life orbiting it, apocalypse is a word without meaning. When Webb's instruments detected light from K218b, that light had been travelling for 120 years. When it began its journey, the year on Earth was 1905. Einstein was writing about relativity. The Wright brothers were testing flight. Our species had barely learned to reach the sky, while that planet had already been breathing beneath one for eons. It means that what we see is not the present, but the past, a memory of a living world as it was a century ago. And when we look again, decades from now, we will still be catching up to that moment. Astronomy is always a conversation across time, and the universe speaks slowly. Yet even a whisper from 120 light-years away can rewrite everything we believe. The chemistry in that air, the mixture of gases, the imbalance that only life can maintain, dances to the steady beat of its star. The red dwarf provides a constant rhythm. The planet answers with metabolism. Together they form a perfect loop, one stable, one alive. It is a relationship of opposites, a duet between fire and breath. The star gives constancy. The planet gives change. One burns, the other renews. Our own world began in chaos. Fire and impact, the violence of a young system. But around a quiet red dwarf, life could begin in peace. The glow is faint, but for a planet like K218b, it is enough. Enough warmth for oceans, enough light for chemistry, enough time for everything. Perhaps that is the universe's quiet truth, that life does not crave brilliance, only balance, that it can bloom under crimson skies as easily as under blue, that existence itself is adaptable, universal, patient. So when we look toward Leo and see that faint red spark, we are not seeing emptiness. We are seeing endurance. A sun that has been burning softly for billions of years and will burn for trillions more. And beneath its calm glow, behind curtains of hydrogen and mist, a living world may still be turning, slowly, silently, in the light of an immortal star. The light from K2-18b's red sun filters through layers of hydrogen and vapour before it reaches the oceans below. To the human eye, those skies would not be blue but pale amber, shading to deep rose near the horizon. Clouds drift slowly, broad and dense, tinted by the faint copper glow of the star. The air itself would shimmer, heavy, rich, almost luminous. A living lens of gas that both shields and sustains what lies beneath. This atmosphere is the planet's great architect. It is not thin and fragile like Earth's, but vast and thick, hundreds of kilometers deep. Hydrogen dominates, laced with carbon dioxide, methane and water vapour. Together they create a powerful greenhouse, yet not a destructive one. Instead of scorching the surface, the heat spreads evenly, keeping the world in thermal equilibrium. Water neither freezes nor boils, it simply endures, flowing through endless cycles of vapour and rain. From orbit, the upper layers appear calm, but deeper down the air grows dense enough to blur the line between sky and sea. The clouds merge with mist. Mist dissolves into ocean. The boundary of air and water is not a surface but a gradient, a slow fading of one into the other. Beneath that soft veil, sunlight weakens, replaced by a crimson glow that seeps through like light through stained glass. The ocean itself may be hundreds of kilometers deep, far beyond any pressure our submersibles could survive. Hydrogen mixes freely with water, creating a liquid unlike any on Earth. Lighter, more compressible, able to remain fluid across an enormous range of temperatures. It is a sea where chemistry reigns supreme, a cradle of molecules that might assemble, divide, and breathe. If life exists there, it likely began in those depths, far from the reach of light. On Earth, we once thought sunlight was essential to creation. But at the bottom of our own oceans, near volcanic vents, we found entire ecosystems that thrive in darkness, powered not by light, but by chemistry. They live on heat and minerals, on gradients of energy rather than rays from the sun. The same could be true on K218b. Its oceans may harbour hydrothermal fields where hydrogen and carbon mingle, giving rise to the first spark of biology. The pressures down there would crush steel, yet for living cells, pressure can be protection. It stabilizes fragile molecules, drives reactions, and keeps water liquid even when the temperature soars. If microbes ever took hold in those depths, evolution would have had billions of calm, stable years to perfect them. Webb's instruments can't see that far below the clouds, but the atmosphere above betrays what happens beneath. The gases we detect, methane, carbon dioxide, traces of dimethyl sulfide, suggest an active cycle connecting sea and sky. On Earth, that balance is maintained by life, algae producing methane, microbes consuming it, plants exhaling oxygen. On K218b, something similar could be at work, though shaped by very different rules. The absence of ammonia is another clue. On dead planets, ammonia tends to build up over time, a leftover of chemical decay. But here, it's missing, likely converted into more complex compounds or broken apart by living metabolism. Even without seeing a single organism, the atmosphere behaves as if it is being constantly adjusted, tuned, and renewed. Imagine standing, or perhaps floating, somewhere within that environment. The air would be dense enough to feel like water around you. Sound would travel slowly but clearly, vibrations passing through the fluid medium in deep, resonant waves. A single drop of the ocean would contain more pressure than the deepest point of the Mariana Trench. Yet to native life, it would feel natural, balanced, serene. Light would fade quickly with depth. A few hundred meters down, the world would turn red-black, illuminated only by faint chemical luminescence, life's own answer to darkness. Perhaps tiny organisms drift there, glowing softly, exchanging heat and light as language. Perhaps immense slow creatures glide through the warm abyss, sensing one another through electric fields and pressure waves. Every breath of that ocean would be chemistry in motion. Methane rising from the depths would mix with carbon dioxide from above, producing new compounds that feed microscopic life. Hydrogen dissolved in the water would serve as both shield and fuel. On Earth, such chemistry builds cells. Here, it might build something stranger, biology that doesn't rely on oxygen at all, and yet in many ways it would still feel familiar. Wherever we find life, we find balance. Energy flowing in cycles, waste becoming food, stability maintained through constant change. That is exactly what Webb has seen in the ratios of gases high above the planet's clouds, a living system regulating itself. In the mid-layers of the atmosphere, temperatures and pressures resemble those near Earth's surface. If any part of K218b could host organisms similar to ours, it would be there, suspended in the air like plankton in an invisible sea. Tiny microbial colonies might drift with the currents, feeding on trace chemicals, absorbing light from the red sun. Each one would be a speck of life carried by the winds, rising and falling through a planet-wide ocean of air. We already know such worlds can exist. In the clouds of Venus, scientists have found patterns of chemistry that hint at microbes floating high above the surface. K2-18b's atmosphere is far gentler. No acid storms, no suffocating heat, making it an even better candidate for aerial life. If the oceans below are the planet's heart, its atmosphere is the breath. Every molecule of methane or dimethyl sulfide that escapes the sea becomes a message, drifting up into starlight. Those molecules crossed space and touched Webb's mirrors, carrying with them the unmistakable rhythm of metabolism, the pulse of an alien biosphere. The beauty of this discovery is that we can read that message without ever leaving home. We can sit on a quiet world orbiting our own star and through light alone reconstruct another world's climate, chemistry, and perhaps its biology. From the tiniest distortions in a beam of infrared, we can tell whether another ocean ripples, whether another sky holds rain. And rain it surely does. Water vapour in K2-18b's atmosphere forms massive clouds that rise and fall in slow convection. As they cool, they release showers that fall not as drops but as sheets, thick as mist, gliding through the air until they vanish into deeper layers. There, the pressure is so high that the rain may turn to liquid metal or crystalline ice before sinking into the ocean below. Every stage of water, vapour, liquid and solid could exist simultaneously, stacked in layers like pages of a cosmic story. That cycle, evaporation, condensation, rainfall, is the same one that shaped Earth's weather and nourished its life. It's a reminder that even across light years, the language of nature is universal. Chemistry follows the same grammar everywhere. The deeper scientists look, the clearer it becomes that K218b is not just habitable in theory, but dynamic in practice. The planet breathes, it recycles, it changes. Each new observation reveals motion, feedback, adaptation, the hallmarks of a living system. Somewhere below the clouds, in the pressurized warmth of those alien seas, evolution may have already taken remarkable forms. Simple cells could have merged into colonies. Colonies could have learned to sense, to move, to think, all at a pace measured not in millions of years, but in billions. The red dwarf's slow heartbeat allows evolution to unfold without interruption. We will likely never see them directly. Not yet. But the air they exhale, the molecules they release, have already reached us. Tiny signatures of existence carried across space. They are proof that we're no longer just observers of the cosmos, but participants in its oldest conversation, the exchange between light and life. As the James Webb Telescope continues to gaze at this world, every photon it captures brings us closer to understanding the unseen. The next step will be to map the layers of that atmosphere in even finer detail, to measure how the light shifts, how the winds move, how the chemistry evolves from year to year. For now, though, it is enough to know this. Somewhere beneath a crimson sun, beneath clouds that shimmer like silk and oceans that never end, there is balance. A living equilibrium between heat and cold, air and sea, star and planet. It is a balance so perfect it almost feels intentional, not designed, but inevitable, as though the universe itself seeks life wherever it can. And on K218b, it may have found one of its most enduring homes. A world breathing softly in the light of a red star, a world whose oceans remember the first warmth of creation, and whose sky carries the quiet, steady pulse of life. For centuries humanity has looked up at the stars and seen only silence. And then came K218b, not the twin of Earth we expected, but something more mysterious. An ocean world shrouded in hydrogen, orbiting a red sun far from anything we've ever called home. Its discovery didn't just expand astronomy, it expanded imagination itself. Because for the first time in history, we're not just wondering if life exists elsewhere, we're seeing the signs that it does. When Webb's golden mirrors revealed the faint traces of dimethyl sulfide, it was more than data. It was a tremor in the human story. In a few lines of spectrum, the silence of the universe cracked open, not with sound, but with evidence. That single molecule bridged a chasm between worlds. It said, quietly but unmistakably, you are not alone. The meaning of that cannot be measured in percentages or confidence levels. It reaches deeper than science, into philosophy, art, belief, and identity. It forces us to see life not as an exception, but as a principle. For generations we thought existence was rare, that biology was a cosmic accident born of perfect conditions. But Earth has never been the only stage where the laws of chemistry play out. They've been performing across the galaxy for billions of years, everywhere matter finds the balance between energy and order. We have already seen the hints. Microbes thriving in nuclear waste, bacteria sleeping for millennia beneath Antarctic ice, creatures living kilometers under the ocean, feeding not on sunlight, but on the heat of the Earth itself. Life, it seems, does not wait for comfort. It thrives in defiance of it. And now, 120 light-years away, a world breathes under a red sun, proof that existence is not fragile. If K2-18b hosts life, it reshapes everything. Because red dwarfs, like its parent star, are the most common suns in the Milky Way. For every star like our sun, there are 1,000 like it, smaller, older, steadier. If even a fraction of them hold planets like K218b, then the galaxy is not silent. It is teeming. Billions of worlds, billions of beginnings. The implications stretch far beyond astronomy. They reach into the very equation that tries to measure our cosmic solitude, the Drake equation. For decades, it was a thought experiment, a fragile attempt to guess how many civilizations might exist. Now, one of its most uncertain variables, the likelihood of life emerging, has shifted from a question mark to a near certainty. Life, it seems, doesn't wait for Earth-like conditions. It emerges wherever chemistry and time are given room to work. If biology can breathe hydrogen, if oceans can live beneath red suns, then the definition of habitable becomes almost universal. It changes how we see ourselves. For most of human history, our stories put us at the centre, chosen, unique, surrounded by divine emptiness. Then came Copernicus, who moved the Earth from the centre of creation. Then Darwin, who placed humanity within nature rather than above it. And now, Webb, which has moved life itself from the realm of miracle to the rhythm of physics. We are not an exception. We are an expression. One verse in a song that began long before us and will continue long after. And yet, this realization does not diminish us. It connects us. It means that the atoms in our bodies, forged in dying stars, may also breathe and think elsewhere. The same chemistry that flows through our blood may flow through alien oceans. The same physics that ignited our sun lights a trillion others. The James Webb Space Telescope has become our new sense organ. Not eyes or ears, but something deeper. A way to perceive life through light. Each photon it captures is a syllable in the language of existence, travelling for over a century to reach us. And it's not alone in its search. Other observatories, the Nancy Grace Roman Telescope, Ariel, LUVOIR, and future ground-based giants, are already being built to continue the hunt. Soon we'll be able to analyse not just one world, but hundreds. If even a handful show the same chemical imbalance, the same whispers of metabolism, then life is not a miracle. It's a pattern. Imagine the night when we realise that every constellation hides a living world. Each faint star, a sun with oceans, clouds, and chemistry of its own. Some of those worlds may be primitive. Others could be ancient beyond comprehension, their civilizations having risen and fallen before the first humans carved stone. But even if we never meet them, their existence changes the meaning of ours. Because for the first time we know that life on other worlds is much more easily accessible than we thought. For philosophy and faith alike, this discovery reframes everything. If life fills the galaxy, then creation itself is not selective. It is abundant. The sacred becomes not something that happened once, in one place, but something that happens everywhere matter organizes itself. The miracle is not that life exists here, but that the universe allows it everywhere. And yet, this revelation carries a mirror. We have found proof that life may thrive under alien skies, while ours, under a bright yellow sun, trembles under the weight of our own making. K2-18b is balanced, steady, enduring. Earth, by comparison, feels restless and fragile. The universe has shown us what sustainability looks like, not as a political ideal, but as a natural law. Perhaps this is the real lesson of K2-18b, that survival is not about domination, but about equilibrium. Life lasts longest not when it conquers, but when it cooperates. When historians of the future look back, they may call this the moment when astronomy became biology, when we stopped studying light and started studying life through it. Webb's golden mirrors, hanging in the void a million miles away, have become bridges, linking our small blue world to something vast and enduring. Because even now, as Webb listens, our own signals are moving outward. Radio waves, television broadcasts, the digital heartbeat of our civilization. They're expanding through space at the speed of light, crossing the distance to K2-18b and beyond. Somewhere, if that world truly breathes, our signals may already have arrived, and perhaps on its crimson shores something alive has paused, sensing a faint pattern, a rhythm in the static, a sign that it too is not alone. If that moment ever comes, if two worlds separated by 120 light-years recognize each other's presence, it might be the greatest conversation in history. Not in language, not in sound, but in light. Until then, what Webb has shown us is enough. Enough to know that the universe is not silent but full of hidden songs. Enough to know that life is not fragile but inevitable. Enough to remind us that every molecule of air, every drop of ocean, every breath we take connects us to something older and greater than ourselves. And as Webb continues to gaze into the dark, collecting the faintest whispers of alien seas and skies, we begin to understand the truth that has waited so long for us to hear it. The cosmos is alive. The discovery on K2-18b is not an ending. It's a beginning. The first measured hint that life may not be confined to Earth. From this moment forward, the question changes. We no longer ask if life exists elsewhere, but how many forms it might take, and how far it extends. Science is already shifting. For the first time, astronomy, chemistry, and biology are merging into one discipline, a search for patterns that define life across the galaxy. Researchers call it comparative astrobiology, the study of atmospheres, climates, and chemistry as a connected system. No longer isolated dots of light, planets are becoming data points in a living map of the cosmos. On Earth, new laboratories are recreating the conditions of alien worlds. Pressurized chambers mimic the dense hydrogen skies of sub-Neptune planets, testing how carbon, nitrogen, and water behave under temperatures and pressures unknown to Earth. Some experiments run for months, watching molecules evolve into complex organics that may one day help explain how biology begins anywhere. Others focus on the chemistry of equilibrium, searching for the point where pure physics gives way to metabolism. The goal is to build a library of biosignatures, a catalogue of what living atmospheres truly look like, no matter their composition. Artificial intelligence is quietly becoming the interpreter of this new astronomy. Machine learning systems trained on Webb's data can recognize molecular patterns invisible to the human eye, faint combinations of gases, seasonal fluctuations, tiny variations in brightness that might indicate weather or growth. What once took months of manual analysis now happens in minutes. Each new dataset refines the algorithms further, teaching machines to detect the smallest chemical heartbeat in the vast noise of space. Around Earth, a new generation of telescopes is preparing to take the next steps. The Nancy Grace Roman Space Telescope, launching later this decade, will identify thousands of exoplanets and provide the first large-scale census of their types and orbits. Europe's aerial mission will follow, studying the atmospheres of 1,000 of them in detail. On the ground, the extremely large telescope in Chile will combine adaptive optics and massive mirrors to measure the isotopic makeup of distant skies, subtle ratios that can reveal whether a planet's gases come from geology or biology. Together, these observatories will form an interlinked network, a planetary survey system turning distant points of light into measurable, comparable worlds. The next leap will not be in data, but in vision. Engineers are developing new optical technologies, coronagraphs, and deployable starshades, capable of blocking a star's light so completely that the dim reflection of its planet becomes visible. A single pixel of that light can reveal colour, cloud cover and rotation. With enough pixels, we might one day see continents or oceans glinting under an alien sun. Concepts like NASA's HabEx and LeVoir missions could make that possible within decades. These telescopes would not only detect life's chemistry, but observe its climate in motion, seeing seasons, storms, and the slow rhythm of alien weather. Farther into the future, another vision takes shape, using the sun itself as a telescope. At a point more than 550 times farther from the sun than Earth, gravity bends light from distant stars into focus, creating what physicists call the solar gravitational lens. A small probe sent there could use this effect to magnify a planet 1 billion times, resolving details as fine as mountain ranges. Reaching that distance would take decades, but the technology is within reach of 21st century engineering. While telescopes study from afar, propulsion research looks ahead to the next frontier, not just seeing other worlds, but reaching them. Concepts like Breakthrough Starshot propose fleets of laser-driven nanocraft travelling at 1/5 the speed of light. Their first targets will be nearby stars such as Alpha Centauri, but the same methods could eventually send microprobes to worlds like K218b. Closer to home, new propulsion systems, fusion drives, advanced ion engines, solar sails are being developed and tested in missions across our solar system. Each experiment in deep space navigation, each test of autonomous control, brings the technology of interstellar flight closer to reality. Yet the future of this discovery is not only about distance, it's also about understanding what it means. As more planets reveal traces of chemistry that suggest life, scientists will begin to study not single examples, but the statistics of existence. What does life prefer? Red stars or yellow ones, deep oceans or shallow seas, isolation or complexity? By the middle of this century, the study of life beyond Earth may no longer be a matter of rare finds, but of pattern recognition, biology seen at a galactic scale. This knowledge will not remain confined to astronomy. The same models used to understand other worlds can help us preserve our own. Studying atmospheric balance elsewhere sharpens our grasp of climate feedback here. How gases stabilize temperature, how oceans regulate heat, how fragile equilibrium can be. In learning how other planets maintain life, we may learn how to keep ours alive. The implications extend further still. If we confirm life beyond Earth, even simple microbial life, it will redefine the ethical landscape of exploration. The Outer Space Treaty of 1967 was written before such discoveries were possible. It governs territory, not biology. New policies will need to protect alien ecosystems from contamination and exploitation, ensuring that contact means cooperation, not consumption. For the first time, space law may have to recognize the rights of life itself, however small or unfamiliar it may be. Beyond law and science, this search will reshape how civilization sees itself. For centuries, humanity has imagined the cosmos as a stage for human progress, a vast emptiness waiting to be explored. But as evidence grows that life exists elsewhere, that narrative changes. The universe becomes not a backdrop but a community, a network of living worlds, each shaped by the same forces that shaped us. Our purpose may shift from conquest to connection, from expansion to preservation. Children born in the coming decades will grow up knowing that the night sky is not silent. Every star they see could host oceans, air, and the slow rhythm of biology. Their maps of the cosmos will not end at the solar system, but extend naturally into the living galaxy. The question that defined generations, "Are we alone?" will fade into history, replaced by a new one. How do we fit within this greater web of life? For now, the work continues quietly. Each new observation adds a line to the story. Each new mission extends our reach. The data will accumulate until patterns appear that no one can deny. And somewhere beyond those numbers, in the faint glow of red stars and distant oceans, we will finally see ourselves, not as observers, but as participants in the same universal process. K2-18b was the first to whisper. Others will follow. Each will remind us that life is not a singular miracle, but a recurring theme in the language of the cosmos. The telescopes we build next will not just look deeper, they will listen better, tuned to the faint harmonies of living chemistry across space and time. The future of discovery will not be measured in miles or even in light years, but in understanding, in how deeply we grasp the continuity between Earth and everything beyond it. And when the next signal comes, when another world joins the growing list of the living, we will recognize it instantly, because we will have learned to read the signs, not as distant wonders, but as reflections of a shared origin. The search will never truly end. Each answer will open another horizon, each discovery another question. But this is what exploration means. Not reaching the end of the unknown, but continually expanding what it includes. And in that expansion, we begin to glimpse the real future. A civilization that sees itself not as the center of the universe, but as part of its living edge. In the end, discovery often feels less like revelation and more like recognition, a distant echo of something we already knew. For centuries, we looked into the night sky and wondered who might be out there. Now, we look and realize they were always there. We just hadn't learned how to listen. The light from K2-18b began its journey before any of us were born. It crossed the gulf of interstellar space while humanity was still learning to leave the ground, carrying within it the faint trace of air, water, and breath. When it finally reached us, it changed what it means to be human. We once believed the universe was silent and empty, an expanse to be conquered or explained. But Webb showed us that silence can be deceptive. The universe is not mute. It speaks in chemistry, in the shifting ratios of gas and light, in patterns that whisper of balance and renewal. Life, it turns out, is not an anomaly. It is a natural way for the cosmos to know itself. That realization reshapes everything. It tells us that the boundary between us and them, between Earth and elsewhere, is thinner than we imagined. The same processes that gave rise to plankton in our oceans may be at work beneath a red sun in Leo. The same laws that shape the air we breathe shape the clouds above alien seas. For the first time, our technology has reached a kind of empathy, an ability to sense the existence of something living without ever touching it. We are learning to understand life not by seeing it move or grow, but by hearing its rhythm in the light of distant stars. There will be more discoveries, more signals, some clear, some uncertain. Each will remind us that we are part of a much wider story, a story not of isolation, but of connection. And each time a new world reveals its chemistry, it will feel a little less foreign and a little more like home. One day, centuries from now, explorers will stand on the shores of other worlds. They will see skies coloured by unfamiliar suns, oceans that never knew our moon, mountains that rose without our gravity. But in those landscapes, they will find something familiar, the unmistakable logic of life adapting to survive. And when they look back toward the faint blue point of Earth, they will understand what Webb began. That the search for life was never about finding others. It was about understanding ourselves. Because in every spectrum, every equation, every photon that crosses the void, there is a shared truth. Life is not fragile. It is persistent. It is creative. It is the universe's most eloquent form of continuity. The first breath on K2-18b, the first molecule that learned to replicate under a red sun, may have been the echo of the same principle that shaped us. Different chemistry, same idea. Survival, adaptation, awareness. When that light reached Webb's golden mirrors, it completed a circle billions of years in the making, the cosmos observing itself through the eyes of one of its creations. That is what makes this moment more than discovery. It is a reunion. The stars are no longer distant. They are familiar, not because we have gone to them, but because we now know they live. And so the search will continue, not driven by loneliness, but by kinship. Every telescope, every mission, every experiment will add another note to the same quiet melody that connects all living things. The universe was never empty. It was waiting for something that could see and wonder and finally understand. If you liked the video, don't forget to leave a like and subscribe. It makes a huge difference and helps the channel grow.